but it could only explain a particular point in the in a particular point of time. Then you needed the Planck's law of distribution, and then quantum mechanics was born. So that was a new way of doing the same thing about special theory of relativity, general theory of relativity, and many things that we learn in physics or even in mathematics. That's how, for example, group theory is an abstraction coming from the standard multiplication and so on. So we adopt the same procedure here, and I will define the linear vector space. Consider a set and I will represent the member of the set they will be called abstract vectors. We will define two operations addition is one and scalar operation is the other. So we do it this way. If x are in S, then there is a rule for addition, which I will use this symbol. For every x and y in S, this has to be done. This definition has to be given from outside.
Sir?
Yes.
Can you write the letters bigger?
Pardon?
Can you write the letters bigger?
Yes, please.
Okay. When
Can
you
you
are
put
writing.
In the chat mode, let me see.
Okay, fine.
Professor, it is visible only, sir. You can.
No, please put whatever question you have in chat mode so that I see. Please write bigger. Okay, I will do that. Okay. So this is addition. Let me redo that. Is this size okay?
Ah, yes, sir.
Okay. The other one is, what are the properties this should have? Commutative. This is also vector in S. The same way, this should be the same vector in S. Associative. X, Y, Z in S. Okay. The third one, 1 into X is X. This is the multiplication. Then alpha into X is in X, is in S, and alpha beta is equal to alpha beta. Alpha and beta are real or complex numbers. Depending on the space that we are talking about. Okay. Pi alpha plus beta on X equal to alpha X plus beta X. 6 alpha Now, we have defined what is an abstract space, abstract vector space, but we have not yet defined the linear vector space. That is the next thing I will do. Beyond all this, there exists a null vector zero such that in NS such that for all then for every X in S there is a reverse X prime such that X plus X prime is equal to 0. These are the things which we need for defining an abstract linear vector space. This is stage 1. Now I will give some examples. set of complex numbers. So Z1 is a member of S. And what is Z1? X1 plus I, Y1. This is the real part, that is the imaginary part. Then it will, you can verify that it will obey all these relations. So I will put it like that here. And this will be the one-to-one correspondence between the two. Now I can do another. I make an n column vector like this. And write down here numbers alpha 1, alpha 2, alpha. Alphas are complex numbers. So I will call this alpha vector. So if I write down alpha plus beta, I will write beta 1 for the beta vector. The addition will be the addition associated with the complex number for each member in this column vector. Similarly, if I multiply by 10, I will multiply by 10 each one of them. And you will find that all the rules are there. And the zero vector would be entry 0, 0, 0. And for this, the minus alpha prime, the reverse would be minus alpha 1, minus alpha 2, minus alpha n, which is also equal to minus 1 times alpha. Okay. Now, I will write down two results for which you will have to do the work and prove that result. 1. 0 is unique. There are no two zeros. Similarly, reverse vector for x is unique. The way you prove this is my problem 1. Yes, assume the contrary. Assume it is not unique and then show that that is not possible. The same way here, assume that there are two reverse vectors for x and just use these properties to show that the two have to be identical. It cannot be different. Okay. What I will do, of course, there are just too many people for us to look at it grading. I will send the solution to Dr. Vijay Raghavan, and he will circulate it to you people at the end of the 5 days. These are standard book work, but still it's worthwhile going through it by yourself. Next, I'm going to do is scalar product. We know in ordinary three-dimensional vector, which we learned, position vector and so on, if A is a vector and B is another vector, A dot B is a number. The one we deal with is normally a real number. And we know how to calculate this in various different ways. Physically, I can say length of A times length of B times cosine of the angle between them, or I can write it in terms of components, AX dx plus AY by plus AZ dz. Instead of doing that, now I'm going to define scalar product explicitly for a linear vector space. I need two vectors in my linear vector space. So I have, and the scalar product is a complex number because we are dealing with, and we will write it as x, y. This is a scalar product of x with y, of x and y. It's a complex number. With the following property: 1, x, y, complex quantity. 2, if z is alpha x plus beta y, then this is the other one. Third, this is slightly confusing notation, but this is the notation which Joglekar has followed, so I'm also following that notation. Just 1 minute, please. This is slightly confusing, but keep it in mind, that's the way it is. All right. Now again, I will write down examples. Before I do that, I want to write one more result. It is this. If z is alpha x plus beta y, this one, then I have this expression. So I can write down this complex conjugate as z w, which is alpha star x w plus beta star y w, which I can write as this should be true for any w. Therefore, I get compare it with this. I take this state, converted this into a vector of this nature, This is usually called the ket vector and this is called the bra vector. I have to complex conjugate these two numbers. And the space generated by this is called the dual space. Just like this is the linear vector space V, that's a different space. And it is called the dual space. Examples. Right now, I'll just give one example because I want to cover a reasonable amount of material. I consider my alpha to be alpha 1, alpha n, beta, then I write which I will write quite often as like this. Write a row vector and use the standard matrix multiplication. Alpha 1 star beta 1, alpha 2 star beta 2, alpha n star beta n, and that is this result. Okay. Notice one thing. Take alpha alpha. This will be sum of I going from 1 to n, alpha I star alpha I, which of course is I going from 1 to n, alpha I squared. Now, when will this be 0? This, if this has to be, these are all some positive numbers, positive or 0. The only way in which this whole thing can be 0 is alpha 1 is 0, alpha 2 is 0, alpha 3 is 0, and so on. So this is greater than equal to 0 and is 0 only if alpha is 0, 0, 0. All right. Now I will come to a very important result. The Cauchy-Schwarz inequality. All this I'm sure you're familiar with, but still I thought I will start from here and then read to things which normally we don't get a chance to teach in MSc classes. X, Y in V, X, Y naught squared is less than or equal to X, X, Y, Y. In ordinary vector space, this makes a lot of sense. What is the left-hand side? Left-hand side is A dot B squared, which is in ordinary vector space. This is A mod squared, B mod squared times cos squared theta. And what is this? That side is A squared and B squared. So this statement is equal to saying a squared b squared cos squared theta is less than a squared b squared, or cos squared theta is less than equal to 1. And when will it be equal to 1? When theta equal to 0. When theta is 0 means a and b are in the same line, in the same direction. But this is a more general statement for b. And let me not prove it. Here, this is an important result. And the proof of it goes the following way. And let me explain. And I'll just write down. I will not give a full proof here. Z be equal to x plus or minus alpha yx y. Just take this definition and do with alpha here. And then use the fact that z and z is greater than 0. And substitute here, and you will get the following result. And square it. You get the result. X plus alpha squared yx mod squared yy minus 2 alpha yx xy. And this must be greater than 0. Why? Because we are substituting for a z in this and get that. This alpha squared. Okay. So this is a quadratic in alpha, and if something has to be greater than 0, then the quadratic in alpha, if I plot alpha here and the function of alpha, quadratic in alpha, it should not cross this. If it crosses this, then the solution will be such that there will be values for f alpha which will be negative. So I'm not allowed to do that. Notice when alpha becomes very large, this is positive, so it is here. So it should never come down. And that means the standard notation b squared minus 4ac must be less than 0. Because where it will meet the axis here will be for imaginary values of alpha. So given that, one can immediately calculate this and get the Schwarz inequality. I'm skipping steps here, but that's a great idea. Okay, just this is my A and this is my B, and this is my C. In my A alpha squared minus B alpha plus C is greater than or equal to 0. Then I use the condition B squared minus 4AC should be less than or equal to 0. And that will lead you to this condition. Okay. Now I'm going to write down the metric space. Let me just wait for a minute here, just to be sure there is nothing in the chat mode. Let A, B be real numbers. Rho AB is a metric. If rho AB is not negative, rho AB is equal to rho BA, and rho AB is 0 only if A equal to B, and rho AA is 0. This is the distance, and the last one is the triangle inequality. Which is rho AB plus rho BC is greater than equal to rho. In linear vector space, you define rho AB as A minus B times A minus B, a scalar product here to the power half and with positive square root. One can verify. Notice when A equal to B, this becomes 0. So this entire thing is 0. And if I put this must be 0, the only way in which it can be 0 is that this be 0. And so A is equal to B. And I have taken that. Triangle inequality I will not verify. I will leave it as a problem. Now comes a very, very important concept in linear vector space.
Professor, please wait. They are copying, I think.
Yes, sir.
I think some of the members are writing, sir. Please wait.
I can't hear you.
I think some of the participants, they are writing, sir. They are copying.
They are copying it down.
Yes, Professor.
No, can you please put it in chat mode, Dr. Vijayaraghavan?
Yes, sir.
I'm waiting for you to put it in chat mode.
Yes, sir.
Now comes the very important concept of linear independence of vectors. Let me firstly explain this. Yeah, Dr. Vijayaraman, I'm waiting for you to put it in chat mode.
Yeah, it is already posted in chat box, sir.
I have not seen it. It just says, please write bigger. Oh, sure. I will wait. Yeah, I didn't understand. I thought because it is recording, I will certainly wait. Normally, I do that when I know students are taking notes, but this time I didn't do it. I will be careful. Okay. Now, I will firstly physically explain what is happening. Take two dimensions, my x-axis and y-axis. If I will draw vectors only starting from the origin. If I take a vector like this, another vector like this, I can never add them by multiplying scalar multiplication and get to 0. Because if I scalar add it would give me this. And if I take it in the opposite direction, it will be a vector like that and it will be like this. So it will never be 0. Let us see what does it mean. Supposing this is 3i plus 4j. This is my vector 1. Let's call this vector b. B is 3i plus 2j. This is smaller. B, I'm going to write it as B is here 2i plus 4j. Now, if I want to add any component, write C1b plus C2a equal to 0. The only solution for this is C1 equal to 0, C2 equal to 0. Let's check. If I do that, if I put here for B, I get 2C1 plus 3C2 equal to 0. And here I get 4C1 plus 2C2 equal to 0. So multiply this by 2. That will give me 4C1 plus 6C2 equal to 0. I subtract from here. I get 4C2 equal to 0. So I get C2 is 0. If I put C2 equal to 0, C1 is also 0. So, if this is the physical thing, A and B are not pointing in the same direction. They are pointing in a different direction. And so I can never increase the length or make it negative and cancel A. B, I cannot go on increasing its length or in the either direction, hope to cancel A. The only way it will cancel A is you multiply A by 0 and B by 0. They are linearly independent. On the other hand, if I had two vectors in the same direction, or if I had three vectors A, B, and C in my two dimension, then A, B, and C are not linearly independent. I can always make A and B combine in a suitable way to get the third vector C. So they are linearly dependent. This is the basic concept. I will wait here and make sure this is clear. I will write down whatever I have just said. This is an extremely important concept. I will write down whatever I just said. Otherwise, linearly dependent. Let us take an example of linearly dependent one. So I write K1 2i plus 3j plus K2 3i plus 5j plus K3 I plus j. I'm going to do that. That's what I'm doing. Now I'm taking three vectors. I'm writing it down with an explicit example. Now dot this with I. Remember I dot j is 0. I dot I is 1. So I get dot it with I dot gives me 2k1. When I dot it with I just get 2k1. I dot j is 0 plus 3k2 plus k3 is 0. Next, I dot it with j. What do I get? I get 3k1 plus 5k2 plus k3 is 0. Correct? Let me choose k1 to be 1. Then what do I get? I get 2 plus 3k2 plus k3 is 0. And I get 3k1 plus 5k2. So 3k1 is 1. 5k2 plus k3 is 0. I subtract. So I get 1 equal to 2k2. So I get k2 equal to half. And therefore I can get k3 now. What will be k3? So I get 2 plus 3 by 2 plus k3 is 0. So k3 is whatever that comes out to be. It is 5.5. I take it to the other side. 3.5. I take it to the minus 7 by 2. So I have a solution for this without being 0. And yet the total can be added up to 0. And that makes sense, right? These three vectors are in the two-dimensional plane. So in the two-dimensional plane, I have three vectors. So I can always take the third vector and scale the other two vectors up and down to make it coincide with the direction of the other vector, third vector. So this makes it linearly dependent. This is a very, very important concept. Okay. Now we can generalize this to our linear vector space. Vectors x1, x2 are linearly independent if this equation implies alpha I is 0, I 1. Remember the first thing which I wrote down with two vectors A and B, it shows C1 equal to 0, C2 equal to 0. That's exactly what this means. Those two equations, I just manipulated them and showed that. If this happens, they are linearly independent. Otherwise, they are not. Now I'm going to define the dimension of a vector space. I'll wait for a minute for people to copy if they're interested. And then I will do it. I start with the vector, say x1. Then I bring in x2. And then I write an equation alpha 1 x1 plus alpha 2 x2 equal to 0. I will check whether this implies alpha 1 and alpha 2 are 0. If it does, x1 and x2 are linearly independent. So I have two linearly independent vectors. Now I take a third one. I will again check in a similar manner whether x1, x2, x3 are linearly independent. If they are linearly independent, I look for a fourth one. I will go on till I exhaust and I find I cannot find any more linearly independent vectors in that space. If I have n linearly independent vectors, but n plus 1 is linearly dependent, the space dimension is n. Now you can ask the question, I started with a vector and said that the space dimension is n by checking linear independence of that with other vectors. Supposing I had started with a different vector, then maybe my dimension will be a different one. There is a theorem which says that is not possible. Whatever choice you make for the initial vector other than the 0 vector, the answer is it is going to be giving you the same dimension as any other vector in the space. Okay. So let me write all this down. X1, of course, is B. Check. Supposing it is linearly dependent, go to X3, check, and go over all the vectors that are available in the space. And if you find all of them are linearly dependent, the dimension is just 1. On the other hand, if these two are linearly independent, then I go to the third vector. And check again. If it is any choice of X3, if it makes it linearly dependent, the dimension is 2. Okay? And so on. So for an n-dimensional space, I think we will stop here for today. We have made reasonable progress. Tomorrow I'll continue doing this linear vector space and do a few more things. So in the meanwhile, if there are some questions.
Yes, sir. I think one of the question.
Yeah, I'm just checking.
Sir, can I read out?
No, I'm just checking the question. Right. Gopi Krishna, I have a question that can we consider the linear independent vector basis in each dimension to be quantized according to Hilbert's? I don't understand this. That is, now notice what I have done is only for finite dimensional spaces. My n is 10, 12, and things like that. I have not talked about infinite dimensional space. Infinite dimensional spaces require more mathematical tools, and we will not have occasion to discuss that here. There is something called inseparable Hilbert space and separable Hilbert space, and that is the kind of situation that we have. When you mean by quantized, you mean discrete values it can take. Integer, that is, I presume that's what you have in mind. And if that is the case, then you need to restrict your Hilbert space to L-squared spaces, and that's where you will find it is possible to do so in terms of you can write down an infinite number of vectors, but in general it is not possible. They are for non-separable spaces, which is a different story. We will not get into that. I will concentrate on finite dimensional spaces, mainly discuss 2-dimensional and 3-dimensional spaces because of this. We have a very short program. And Professor Ashok Kapoor will be dealing with spin half, and I will also be dealing with spin half in most probably in a way which is which will sort of supplement what he is saying.
Okay. Thank you, Professor.
So I will give you that. I don't have it immediately in mind, a reference to infinite dimensional spaces. Is Ashok here?
Yeah. Yeah. Yes, sir. Professor is there.
Is Ashok here?
Yeah. Yes, sir.
Ashok, can you give him a good reference for infinite dimensional space? Well, this book by Denery and Krasiewski has some. Mathematics for physicists. But Ashok might have some more.
I'm sorry. I will tell tomorrow morning.
Yes, sir. Yes, Professor.
Okay. So tomorrow we will meet again. Bye now.
Yeah. Thank you, Professor. Dr. Amir?
Yes, sir. Yes.
Is there the attendance link? Is there, sir?
Yes, sir. Attendance link is ready. I will just circulate to
Can you
the
post it in the chat
Yes,
box?
sir. Yes, sir.
Participants, can you kindly put the attendance here? We are sending the link. So try to attend all the sessions.
Sir, we have made a WhatsApp group, and in that I will plan to place a link,
Okay, sir. Okay.
So participants, we have made a WhatsApp group for this 5 days course, and your attendance link will be submitted, should be shared through that WhatsApp link. All of you please join that WhatsApp group,
Yeah.
where we will be getting in touch with.
You are sending through the mail, no, sir?
Yes, ma'am. Yes. The invitation link will be sent through email.
Yeah, please check the email. There is a link will be sent by Dr. Amiruddin. You just click and join this group. We'll send the informations through that group. Thank you.
Yes,
Thank you
sir.
so much, Professor H.S. Mani, for his wonderful lecture today. I think tomorrow we have a second day session, morning at 10 o'clock. Tell me, ma'am. Professor, can we wind up?
Yes, sir. Yes, sir.
Mani, sir?
Yes, sir.
Yeah, thank you, sir. Sir, feedback link is
Yeah.
at the end of the session.
Yes.
So at the end of this course, we'll send the feedback link. Once you complete the feedback, then you may get the certificate. Attendance daily, so you have to give that attendance. Like this only, sir, Amir, sir?
Yes, sir. Yes, sir. Yes, sir.
Yeah. So please check the WhatsApp group. We will send the link every day. You have to complete that attendance every day. So feedback link is at the end of the course.
Yes, sir.
Yeah, already sent.
WhatsApp group is about to send, sir, in this 2 minutes.
Yeah. Thank you, sir. Thank you for your feedbacks. Professor, can we leave? Some money, sir. What is there?
Yes.
Yes, sir. Can we wind up, sir?
Yes,
Amit,
sir.
sir?
Yes.
Yeah, thank you, participants. Tomorrow we'll meet.